Hello students, in today's lecture we will learn few more examples of protection and deprotection of alcohol functional groups. Okay, so in my previous lecture we have discussed about the methylation or methyl ethers formation. So for the formation of methyl ether we use dimethyl sulfate, diazomethane or methyl iodide in presence of silver salt. So friends, we'll learn about the methylation as well as we'll learn about the demethylation, or we can say this as a deprotection or cleavage. In presence of BBr3 or HBr in acetic acid, methyl ethers are demethylated. So in this lecture we will see some substituted methyl ethers or some acetals. So in this lecture we will discuss about methoxymethyl, that is MEM protection, methoxyethoxymethyl, that is MEM protection, or benzyloxymethyl, that is BOM protection, whereas we also discuss about paramethoxybenzyl, that is PMB protection and deprotection. Lastly, the fifth protection group is THP, that is tetrahydropyran, its protection and deprotection. So this lecture might be a bit lengthy, so let's discuss about this kind of protecting groups. The first group is methoxymethyl, that is MEM protection. So we can protect OH group of phenol as well as alcohols with the help of methoxymethyl. The protection looks like methoxy, and this is a methylene, or we can say methoxymethyl protection, so abbreviated as MEM protection. So you can see this is the protection of phenol with the MEM and protection of alcohol with the MEM. So reagents used for the protection of alcohols with MEM is methoxymethyl chloride, or abbreviated as MEM chloride, in presence of organic base. So in this case is a diisopropylethylamine. Also we can use MEM bromide in presence of base to protect the alcohols or phenols with the help of MEM chloride. So friends, how the protection happens? You can see there, this is the OH group which attacks on the carbon which is attached to the chlorine, and chlorine displays as a leaving group. So this is how this pink part is attached to the oxygen or OH group. So this is called as methoxymethyl or MEM protection. There are some examples which shows us how it is used for the complex synthesis. So in this example, this OH was protected by MEM chloride in presence of NaI and DIPA, that is diisopropyl ethylamine. So we get the OH protected with MEM, and we get O-MEM, that is methoxymethyl protection of OH. Now in the second example also we have these two OH groups over here. So if we use one equivalent of methoxymethyl chloride or MEM chloride in presence of base, here they use sodium hydride as a base, so we get the protection of one of this OH group with the MEM. So this is how we do the protection, MEM protection. Now let's go for the deprotection. So MEM ethers or acetals are very labile to the concentrated acids. Okay, so in presence of traces concentrated HCl we can deprotect the MEM. Okay, so this is a MEM protected alcohol over here. Okay, this is a O and this is a MEM. Okay, this is MEM protected alcohol, and when we treat it with the HCl, so the OH, this OH is get protonated, and we get the positive charge on oxygen. To neutralize this positive charge, the Cl minus attack on this carbon, which is very electron deficient because of these two oxygens, and as Cl minus attack over here, this carbon oxygen bond breaks and we get the free OH group. Okay, so this is how the MOM is deprotected in presence of traces of concentrated HCl. Even if in the laboratory we wash the glassware with the HCl, and if we do not wash it properly, and if there is a little bit of or traces of concentrated HCl remain in our glassware, this one also deprotect the MOM. So we can use concentrated HCl, or you can use 50% HCl or 6 molar HCl, or sometime we can use TFA, that is trifluoroacetic acid. This is how the MOM is deprotected. Okay, let's go for the another group or examples. So these are few examples of deprotection in presence of concentrated HCl and TFA. So let's go for the another protecting group. So next protecting group is methoxyethoxymethyl. Okay, methoxyethoxymethyl, or abbreviated as MEM. Okay, MEM protection. So MEM ethers are similar to the MOM ethers in their stability to protic acid, but these MEM ethers are sensitive to the Lewis acids. Okay, these are Lewis acids. This is the difference between MOM and MEM ethers. So what is MEM? Let's see what is methoxyethoxymethyl. So this is a methoxy, ethoxy, and then methyl. Okay, this is methoxy, ethoxy, and methyl. So it is called as MEM protection or MEM group. So the mechanism is very simple. Okay, there is some problem with the arrows. So oxygen lone pair will attack on this carbon, which is electron deficient carbon because of chlorine and oxygen, and chlorine will leave as a leaving group. So we get the methoxyethoxymethyl protection. So the most common reagent for the protection is 2-methoxyethoxymethyl chloride. This is the 2-methoxyethoxymethyl chloride. With the help of we get the protection, MEM protection. So MEM is methoxyethoxymethyl or MEM protection. This is a MEM group. This is how the MEM protection is carried out. So let's see the deprotection. So for the deprotection, as we already discussed, the MEM protection is sensitive to Lewis acid such as ZnBr2, FeCl3, etc. Also, it can be deprotected with the help of protic acid such as HBr or TFA. So with the help of Lewis acid, the mechanism is as follows. These two oxygen are coordinate with the metal, or in case this is a zinc, so it coordinates with zinc, and that's why this oxygen, okay, this oxygen provides the electron density to other oxygens. These are some mistakes with this arrow. This oxygen and carbon bond is broken. Okay, this is how the deprotection takes place, and we get the free OH group over here. So this oxygen and carbon bond is broken, and we get the free OH group with the help of Lewis acid such as ZnBr2 as well as FeCl3. With the help of protic acid, the deprotection mechanism is same as that of MOM protection. Okay, in the presence of HBr in acetic acid or HBr, we get the protonation of this oxygen, and chlorine will attack on this carbon. Okay, this is how this MEM and MEM, these three MEM groups are deprotected in presence of aqueous HBr. We get OH, OH, and OH over here. So this is how MEM deprotection is carried out. So far we discussed MOM protection and deprotection, MEM protection and deprotection. Now let's go for another protective group, that is called as BOM group or BOM protection. So sometimes it sounds very funny. BOM stands for benzyloxymethyl. So there is not much change with this substituted methyl acetals or ethers. Instead of this methoxymethyl. So in case of methoxymethyl, this methyl over here or methoxy over here. So in presence in instead of methoxy, now we have benzyloxy. So how the benzyloxy group or benzyloxymethyl group is used for the protection? We use benzyloxymethyl chloride, a common reagent for the protection. This OH group, OH lone pair again attack on this carbon and we get the chlorine as leaving group, and this part is known as benzyloxymethyl or called as BOM protection. So what is the difference between or how the BOM is distinguished from MEM and MOM? So we have this benzyl group, and as we have benzyl group, it is deprotected in presence of H2PDC or H2 palladium. So benzyl deprotection is very famous deprotection. This H2PDC will deprotect this benzyl ethers. So BOM, that is oxygen, is OH is protected with benzyloxymethyl, which is deprotected in presence of H2PDC. You can see here, okay, H2PDC will deprotect BOM to OH. This OH gets free, whereas this THP and methyl ethers are stable in presence of H2PDC. So instead of H2PDC, we can use sodium and ammonia, lithium and ammonia, and so on. So these are the reducing agent which deprotects the benzyl. Okay, this is a simple benzyl deprotection. This is a deprotection mechanism. You can see there is the oxidative addition of palladium in this oxygen and carbon bond. So we get the oxidative addition, then coordination of H2 molecule will coordinate with this OR and palladium. We get free ROH or deprotection, and then we get the reductive elimination of toluene and we recover the catalyst. This is how the deprotection mechanism takes place in case of benzyl. So it is usually for all the benzyl groups. Okay, if we have different types of substituted benzyl groups, the mechanism is same. So I will not discuss much of this mechanism in the next protective groups, because our next protective group is also contains benzyl group. Okay, so our next protecting group is para-methoxybenzyl or abbreviated as PMB. So this is also a benzyl functional group, and you can see benzyl can be deprotected with H2PDC, but these two are very different. We will discuss the difference of deprotection for PMB as well as BOM. So let's first discuss the protection of PMB and how it differs from the previous BOM protection. So if we have OH group, ROH, alcohol group, we can use para-methoxybenzyl chloride. In presence of base, this proton is abstracted and we get, okay, I have mechanism for you guys. We have ROH in presence of base, we get this alkoxide which attacks on the carbon which bears chlorine, okay, and displaces the chlorine, and we get the para-methoxybenzyl protection of this alcohol. So most common reagent used is para-methoxybenzyl chloride. So this group is very commonly used because its deprotection mechanism is very different. So the deprotection of PMB is carried out with the help of DDQ, that is dichlorodicyanoquinone. Okay, dichlorodicyanoquinone is called as DDQ. It is an oxidizing agent. As you know that oxidation is also a removal of hydrogen. So the benzyl hydrogen is removed by the DDQ with the set mechanism or formation of charge transfer complex. So this benzyl hydrogen is abstracted by this carbonyl group, okay, or it is transferred to the oxygen and it is started from the methoxy. Okay, this methoxy oxygen lone pair will delocalize. We transfer this hydrogen to the oxygen and again this oxygen will abstract another proton. So this quinone will convert it to the hydroquinone. This is a oxidizing agent. So once the quinone is converted to the hydroquinone, we get this kind of intermediate having lone positive charge on the oxygen of methoxy group. So this positive charge is neutralized by addition of water to this benzyl carbon. Once we add the water, we get the OH, and then again this OH, the oxygen lone pair is delocalized, and this forms the aldehyde, paramethoxy benzaldehyde, and we get the deprotection of OH group or free OH group. Okay, we get the alcohol back, and the side product is paramethoxy benzaldehyde. This is how this PMB is different than other benzyl protections. Okay, so this is not cleaved by the H2PDC, or it is cleaved by H2PDC, but very commonly it is deprotected with the DDQ. Okay, so with the help of DDQ or oxidizing agent, we can easily remove the PMB protection. So this is also very useful protection for the alcohols. So let's go for some examples. So we can see here the PMB protection, and in presence of DDQ, this PMB is deprotected to OH group. So OME are intact in this condition, but only PMB is deprotected. So I have a question for you guys. If I have paramethoxy benzyl and dimethoxy benzyl, okay, paramethoxy benzyl and dimethoxy benzyl. So I have two methoxy group over here and one over here. So if I treat this molecule with DDQ, what will be the final product? So as we discussed the mechanism, the role of OM is very important for the deprotection. So the firstly, DMB, that is dimethoxybenzyl, is deprotected instead of methoxy group. That proves the importance of OME group in the deprotection. Okay, this is not a simple benzyl ether, this is a methoxy benzyl ether, so which help us for the deprotection of this group. So this is how PMB deprotection and protection is carried out. Now let's go for the last protection group, that is a THP protection or tetrahydropyran. It is very simple functional group or protection group. We have this dihydropyran for the protection. So once we have dihydropyran, so what is dihydro? We have extra 2 hydrogen in this molecule, so this is a dihydro, only one double bond over here. So in presence of any catalytic amount of acid, it gives activated dihydropyran. This is a activated dihydropyran. So this activated dihydropyran is attacked by OH lone pair, and we get this kind of protection is known as tetrahydropyran protection of alcohol. This is a tetrahydropyran group, and now it is protected. So it is looks like methoxymethyl also, but the deprotection mechanism is little bit different. So let's see the deprotection of THP. So THP can be deprotected in presence of acids. The most common acid used is paratoluene sulfonic acid. So paratoluene sulfonic acid have the H plus. The H plus is abstracted by the oxygen lone pair. We get protonated oxygen, and if we have excess of methanol, that is solvent, excess of solvent will attack on this carbon which is in between these two oxygen and very electron deficient. Once the methanol attack on this carbon, we get free OH, we get ROH or deprotection of alcohol from THP, whereas we get the byproduct like this. Okay, this is the byproduct from the THP deprotection. So this is how THP protection is done with the help of dipyromethane, and deprotection mechanism is like this in presence of catalytic amount of paratoluene sulfonic acid, that is PTSA. Let's see some examples. So this is a THP protection, and it is also deprotected in presence of dimethyl aluminum chloride. So this is THP and it is deprotected to OH group, whereas methyl and silyl protection is intact in this condition. So this is how the THP protection and deprotection is carried out. So friends, in this lecture we cover THP protection, MEM protection, MEM protection, BOM protection. So I will suggest you to go for EE, that is ethoxyethyl, and methyl thiomethyl, that is MTM protection and deprotection. These two groups, or these two protection group, we haven't covered in this lecture. So this is for your homework. Go for ethoxyethyl and MTM, that is methyl thiomethyl protection and deprotection. So all these functional group protection and deprotection I took it from